Okay, so this is the last question from the 2023 Intermediate Maths Challenge. And in this question, we get given a large circle. We don't really know anything about it, other than there are two smaller circles which are inscribed within that larger circle, and we've got a chord from P to Q, and its length is 6. So that's all we know, and what we'd like to find is the area that is shaded in on this diagram. So that's the area not taken up by either of the two smaller circles. What I really like about this question is that when we solve it, we use some interesting ideas that can be applied to lots of questions about circles. Let's start off then. Our first thing to do is a technique that is always useful for circle questions, and that's thinking about the one really important measurement for a circle. That's its radius. So let's think first of all about this circle on the bottom. Its radius, drawn like this. We could call this R1. Right, so if we have this is circle number 1, its radius is R1. Let's do the same thing for the circle on the top. Its centre is probably about here. If we call this circle 2, its radius is R2. Straight away when we've done this, we've made a real leap forward, because now we've gone from these circles which we knew nothing about to saying, well, at least we know their radius. Next thing to do is think, can we start putting this together into some maybe more useful information? And actually, we can be sure that these two circles, they lie on a diameter of the larger circle. So what we're going to do is we're going to add in the second radius for each one. So this is another version of R2. And this length here is another R1. So what we've got is 2 lots of R2 and 2 lots of R1. If we think about this, it has to be symmetrical. So these together form a diameter for the larger circle. Let's write this down then. We're going to use a capital D for the larger circle's diameter. And when we add up what we've got 2 lots of R2. So let's call it 2 lots of R2. And what we need to add on is 2 lots of R1 as well. So 2 lots of R2 plus 2 lots of R1. Okay. Diameter's useful, but we'd actually like the radius of the larger circle. That's going to be really helpful for us later. Thinking about the radius of the larger circle, let's add it on in a new colour. Because this bottom circle is the larger of the two, the centre of the larger circle is probably going to be maybe about here. And if we add this into our diagram then, that means this is the radius of the whole circle altogether. Well, radius is always half of diameter. So what we need to do is half this D. Let's call the radius of the big circle, the whole thing, capital R. That's this radius. We need to half 2 lots of R2 plus 2 lots of R1. So that will definitely just give us R2 plus R1. Let's add this onto our diagram then. So this radius here of the whole circle will be R1 plus R2. I've switched the order around, but it's definitely the same thing. This makes intuitive sense to us as well, because we're thinking about the radius of the larger circle, of the whole thing, and that's just an average of the radii of the 2 smaller circles inscribed within it, added together. So it's related to some kind of average of these two. Some next steps then, what could be useful? And now we should start thinking about areas. The area of this whole larger circle, let's think about that first. And we can call this just capital A. Well, for a circle, its area is always pi times the radius squared. And we know the radius of the whole thing is r1 plus r2. So let's write this in. Pi times r1 plus r2 squared. And when we expand this thing out, our r1 plus r2, we're going to get pi times r1 squared plus 2 lots of r1, r2 plus r2 squared. That's our whole area all together for the big circle. Now let's think about our two smaller areas. So if we call for our first circle on the bottom, this will be area 1. And area 1 is just going to be pi times r1 squared. So here we're just going to have pi r1 squared. Our other area to think about should be area 2. That's the area of circle 2 up at the top. And that's just going to be pi, if I can pick up my chalk, pi r2 squared. Okay, our last step when thinking about these areas then is our shaded area. So for this I'm just going to write shaded area. And finding our shaded area, it's our whole circle all together. That's this long area over here. We need to take away area 1 and also take away area 2. Let's write out the whole thing that we've got then. So we've got pi. If we expand out our brackets at this point, we've got pi r1 squared plus 2 pi r1 r2 plus pi r2 squared. That's the area of the whole big circle. We've multiplied the pi out of those brackets. What we need to do is take away area 1 and also area 2. So they're going to give us a takeaway, let's put it here, pi r1 squared, and also a takeaway pi r2 squared. Well, at this point we can see some terms that are really nicely about to cancel out. So let's have a look at which ones do. We've got a plus pi r1 squared, and we've got a take away pi r1 squared. They definitely cancel out with each other. So let's get rid of this term, if we cross it out, and also this term. There's another term which cancels out in a really similar way, and it's this plus pi r2 squared and this minus pi r2 squared. We can get rid of those two as well. So this one can go, and this one can go. And actually, from something really messy, we're just left with this part. Plus 2 pi r1 r2. So actually our shaded area from all of this is a really simple term, which is just 2 times pi times r1 times r2. We're going to come back to this and carry on with the problem once we've cleared the board. So at this point, we know the shaded area is 2 pi times r1 times r2. We can't stop here, unfortunately. We would like to find a numerical value for this shaded area. And this is a good time to think about what we've done so far and what information we can still use. So far then, we've done a lot with the radii of these two circles. but we haven't actually used this chord at all. And we know that PQ, the chord, has length 6. What we're going to do next then is put together some information from our radius and also from our chord length. And this is a really nice idea. So we remember that this is the centre of our circle, and the radius of our large circle, our largest circle, is R1 plus R2. What we're going to add on then is a new radius. It goes from our centre to the edge of our circle, and it's in a new place. So it's this radius here. We know its length must be R1 plus R2. And what's really cool about this radius is that it forms a right angled triangle. So this in here is a right angle. Well, let's have a think about what we know about it. We definitely know this side is R1 plus R2. I will draw this diagram over here as well in a second. We also know that this length here must be 3. And that's because if this is 3 here, then we've got 3 on the other side to make our total of 6 for the chord. What we're interested in then is this missing length here. We need to think about how to find that, because once we have found that, we can then use Pythagoras' theorem to think about how R1, R2, this missing side, and 3 all link together. How could we find that missing side? This is where it would definitely help to draw some more information over here, because it's a bit cramped on our diagram. And the information we've got is this total length. So from the very bottom of the circle up to the point that the chord goes through, well, this whole thing is 2 lots of R1. Or in other words, it's R1 plus R1. 2 of this radius. And the distance to our centre, so if we try and get about the same level on there, the distance to the centre of the largest circle is R1 plus R2. What we'd like to know is this small difference in here. That represents the height of this triangle. So what we're asking is, what's the difference between R1 plus R1 and R1 plus R2? And we can do that just by a subtraction. So we would do R1 plus R1, take away R1 plus R2, and they should be in brackets. And all we've got there is, look, the R1s, these two will cancel out. We would have left is R1 take away R2. Again, that makes sense to us intuitively, because if R1 and R2 were equal, this would be 0. The centre of the circle would be right where these two circles meet. And the larger the R1 grows in comparison to R2, the larger this distance grows. As the top circle shrinks, this moves up and up and up. So let's add that into our diagram. We've got R1 take away R2. That is the height of this triangle. Now let's draw this triangle over here then, just to make it really clear what we're about to do. So we've got a nice right angled triangle where this top side is 3 from the chord. This side is the side we've just found. That's R1 subtract R2. So R1 take away R2. This is definitely a right angle. And over here we've got R1 plus R2 for our hypotenuse. That's because it was a radius, remember, of our largest circle. At this point we can just use Pythagoras. A squared plus b squared equals c squared. We need to be quite good at thinking about expanding out brackets, but it's not too bad. So let's try it. We're going to take 3 for our a, so 3 squared plus r1, take away r2 squared, equals r1 plus r2 squared. This would be a part where you could check these brackets expanding yourself if you're not convinced. I'm just going to kind of whiz through it. So 3 squared gives us 9. Let's draw a line here as well so we're not too interrupted by what's on the other side. 3 squared is 9, and when we expand this left-hand bracket out, we're going to get plus r1 squared, take away 2 r1 r2 plus r2 squared. That's this bracket expanding out to here. And on our right hand side we've got equals r1 squared plus 2 r1 r2 plus r2 squared. Okay, we've done some really good work there, and we're about to see lots of things cancelling out, and this will start to look really nice in a second. On the left hand side of our equals sign, and on the right hand side, we've got an r1 squared, a plus r1 squared. That means they can cancel out. So this one and this one are r1 squareds, they cancel out. We can have a similar thing about to happen with the r2 squared, plus r2 squared on the left hand side of the equals, plus r2 squared on the right hand side of the equals. Let's cancel those out as well then. He can go, and he can go. What we must be careful with here though, is on the left hand side of our equals sign, we've got to take away 2 r1 r2. On the right hand side of our equals sign, we've got a plus 2 r1 r2. They don't cancel out. We need to add 2 more lots of this over to the right hand side. Let's do that. We're going to stick with our 9 then on the left hand side. The 9 is staying, but these 2 r1 r2s are going to add to these 2 r1 r2s, meaning that we have 4 lots of r1 r2. Well, from here, if you remember right back to the start, we would like to know what r1 r2 is. So this tells us if 9 is 4 lots of r1 r2, then r1 r2 is going to be equal to 9 over 4. We've just divided the 4 through. Okay, we are so nearly finished then, because we said earlier the shaded area is 2 times pi times r1 r2. So to finish off, we just need to substitute this into that formula. Let's write down what we've got then. So if we put shaded, area equals 2 times pi times r1 r2 is just 9 over 4. That's what we just found here. So 9 over 4. And then simplifying that fraction, 2 times 9 over 4 just gives us 9 over 2. So we've got 9 pi over 2. And we are done.